Hi everyone. Well, it's been a while since my last video, but things got real busy around here with work and such, so I haven't had time to do it, but now I've got a bit of time. And so in this video I'm going to take a Hall effect sensor, which I used in a previous video, like this one here, a toroid, ferrite material, and a coil of wire to make a current sensor using the Hall effect sensor. But before I get into that, let's have a look at a bit of magnetic theory. So if we take a coil of wire like this, pass a current through it, and you get a magnetic field. As you can see, these field lines around the solenoid here. Now, back in the early 1800s, a man named Ampere played around with coils of wire and batteries and a compass and figured out that there was a magnetic field produced by the current in the coil. And he developed this formula, Ampere's law it's called, which gives you the strength of the magnetic field, and this is the number of turns in the coil, this is the current flowing in the coil, and this L here is the length of the coil. And this symbol here is the Greek symbol mu, or mu sub zero. It's just the permeability of whatever substance is in the core here, and in this case mu sub zero means the permeability of air or a vacuum. And so this gives you the formula for the strength of the magnetic field in the core. If you have some other material inside the core other than just air or a vacuum, you put another factor in here, mu sub r, which is just a dimensionless number, and which could be 1 or less than 1 or greater than 1, depending on the material that's in the core. And generally we want to increase the magnetic flux in here, so we use a metallic material. Iron nail stuck through here would increase the flux by a factor of whatever it is for iron nail. And so as you can see, the magnetic field strength is proportional to the amount of current flowing in the core. And if I can measure that strength of that field with my Hall effect device, then I can measure the amount of current flowing in the coil. Now this formula here gives me the units of the magnetic field in Tesla. Mu sub zero expands to some weird number. But if I want to change it to a different system of units, because I want to get the flux strength in Gauss, because that's what the Hall effect sensor is calibrated in, and makes this my formula easy to use. And I simply replace mu sub zero with 0.4 pi times the relative permeability, of the material in the core. Now, if I were to take this solenoid, the straight inductor, and I were to bend it into a circle, which I won't do, that's going to wreck it, I'll get a toroid, like this. Bending it in a circle or wrapping it around a core like this here will give me the same thing, a toroid. Now, the formula is the same, and I'm using it in units of Gauss as well, over here, the 0.4 pi. And this figure down here, MPL, just stands for medium path length. And what it is basically just the median diameter between these two, the inside diameter and the outside diameter. So this is the median path length, which is the same thing as the length here, but it's just taken down the center of the core. And this is the formula for the flux strength inside the core here, given for the given type of material, which mu sub r gives you. For this one here is a ferrite material, and it has a mu sub r something much greater than 1, and then the mean path length as well. And when you purchase cores like this, the manufacturer will give you that information. It'll tell you what the mean path length is, and also the relative permeability of the core. Now, for me to be able to get inside this core to measure the magnetic flux with the Hall effect sensor, so I want to put the sensor in the core here like this, so the field is passing through the sensor, I need to cut a gap in the core. And that's what I've done down here in this picture. Cut a small gap. Now if the gap length is very small compared to the mean path length of the core, then this formula here will apply, and it simply just adds a bit of length to the mean path length, which is just the relative permeability of the core times the gap length. And so it seems like the core is longer, which then it would reduce the strength of the magnetic flux. So that's what I'm going to do in order to measure the current flowing in this coil. Is I'll have to get a tool here and cut a little gap in here. A little abrasive cut-off wheel and a rotary tool like a Dremel tool will do the job. And so after I've done that cutting and winding the wire around the core, then we can start doing some measurements. So after some cutting with the Dremel tool and a couple of broken discs and a shattered core, I managed to get one core here with a gap in it, and I measured that gap, and it's 0.191 millimeters in width here. And then I was able to wind about 20 turns around the core like this. And so using these numbers, and I chose a core which is right here, an FT3761 core, which is a type 61 material for ferrite material. And these are the characteristics of the core that we're most interested in. The mean path length is 2.32 centimeters, and the relative permeability is 125. So if I were to pass 1 amp of current through the core here, or through the coil here, I would get a flux strength of 120 Gauss when I plug all these numbers in here. So 0.4 pi, 125 is the mu sub r, 20 turns and 1 amp of current, and then the mean path length for the whole core plus the little bit of extra path length added by the air gap equals 120 Gauss. Now, of course, this is a simplification or an assumption that the gap length is small, because as the gap gets bigger, the flux field will actually bulge out of the gap, and you'll have less density inside the core. So I'm assuming that the flux passing through the air gap doesn't bulge away from the core, and when I put the sensor inside the air gap, the Hall effect sensor will intercept the full strength of the flux in the core. As the gap gets bigger, the more flux leaks out of the gap and the less that you'll see inside the core here. So there's a chance of some error in here. Now this gap length is actually a significant length compared to the core, because you can see here it's a pretty small core with a pretty large gap. So I'll expect some kind of error, but anyways, I'll run through the calculations here. So I get 120 Gauss per amp of current flowing through the core. The Hall effect sensor states a nominal 1.4 millivolts per Gauss of field strength. So therefore the output voltage change will be 1.4 millivolts per Gauss times 120 Gauss, which gives me 168 millivolts of change in the output voltage with 1 amp in the coil. Now you remember the Hall effect sensor's output voltage sits at halfway between the bias voltage. In my case I used 5 volts, and so the output with no flux, with no magnetic field on the Hall effect sensor, will sit at about 2.5 volts. So depending on which direction the field is flowing, it'll be 2.5 volts plus 168 millivolts, or 2.5 volts minus 168 millivolts. And so I'm going to set up this coil here in a little circuit where I can test the current, and I can measure the current, or I can test the Hall effect sensor working in the core, in the gap here, where I can measure the current flowing through the coil and the output voltage of the Hall effect sensor. Okay, here is my test setup. This meter here is measuring the output of the Hall effect sensor. Right now there's no flux, no magnetic field, so it's reading about 2.5 volts. It's biased with about 5 volts. Over here is the meter that measures the current flowing through the coil. What I've done here is I've got a big power resistor. It's about 9 ohms, and it's in series with the coil going to a variable power supply. And I chose a resistor here. I have to put a resistor here in series because I can't get the power supply down to 0 volts. It only goes down to 5 volts. And so by putting that resistor in there, I've got a minimum of half an amp of current flowing at 5 volts. And this circuitry here is not being used right at the moment, but it's just an amplifier, and I'll show you what I'm using it for in a bit. I'll show you the schematic of it. And then here is the core, the coil with the air gap and the Hall effect sensor plugged into the middle of it. I'll just zoom in on it so you guys can see what's going on here. So you can see how the it's going to focus on me. A little bit out of focus. Let's just zoom back a bit. There we go. So you can see how the Hall effect sensor is sitting in the core right now. Oops, wrong way. Now let's zoom back out and have a look at what happens. So I'm going to turn on the current flowing through the coil, and you can see there's just over half an amp, and the voltage changed by let's turn off again here so we can get it. So it goes from 2.58. I'm going to write that down. 2.58 is the no magnetic field current or flux voltage reading out of the Hall effect sensor. I turn on half an amp and I get 2.63. 2.63 at half an amp, or 529 milliamps. Now let's just crank it up a little bit here until we get 1 amp exactly flowing through the coil. 9, 70, 80, 90, oops. So that's pretty darn close to an amp. 2.695. 2.695. So when I do the math here, 2.695 minus 2.58, I get 115 millivolts change for 1 amp. So I predicted 168 millivolts change, and that works out to approximately a 25% error, I think. Yeah, it's pretty close to 25%. Now, as I said, of course, there's certainly going to be some error in this circuit. For one thing, the permeability of the core here is specified by the manufacturer to be plus or minus 25% already. So there's a significant error in the permeability of the core. So it could be 125, or it could be more than 125, or the relative permeability could be greater than 125 by 25% or less than 125. Also, my air gap is, like I said, quite large compared to the mean path length of the core. When I get some better cutting discs for my rotary tool, I can cut a much more accurate gap. And so the actual flux that we're measuring here is going to be less because of some of the leakage that I discussed earlier. So I think this is pretty good, even though it doesn't exactly follow the calculations. There's a certain large error in the calculations. This is definitely linear with current. The output voltage of the Hall effect sensor does vary linearly with current, and therefore I can use it as an accurate current measuring device. It works pretty good. And then because the voltage change out of the sensor is quite small, I need to amplify it, and that's what this circuit is here. And I'll show you a little schematic diagram of the amplifier circuit and what it's for. And this is a potentiometer here that I can use to adjust the bias and remove the 2.5 volt bias from the signal, and therefore I get a 0 to plus whatever volt change that represents a 0 to plus whatever current change in the coil here, and therefore making it a very useful current measuring circuit. So here's a schematic of the circuit that I used, that I just showed you. Initially I just had a meter connected directly to this pin here on the output of the Hall effect sensor, and an ammeter in series with this circuit here. So we've got a variable power supply connected to here and 20 turns of wire around this FT3761 core with an air gap in it. The Hall effect sensor is stuck inside the air gap, and I just vary the voltage here to give me a variable current through the coil. And then this is the amplifier that I'm going to use in order to make the circuit more usable, because 168 millivolts of change here is pretty small, so I want to amplify that with this amplifier here. So I just took a cheapy run-of-the-mill LM358 dual op amp and wired it up to the breadboard here. This is there's two amplifiers in one package. This is the second amplifier. I've just simply shorted the two inputs together and grounded them to just keep the signal noise down on this extra op amp. If these were open, this output could oscillate with a lot of noise and actually affect this one as well. And so I've wired up like an instrumentation amplifier here. The signal from the Hall effect sensor goes into the positive input, and the negative input here comes out of this variable resistor to give me a variable voltage on the input here. And I use this potentiometer to take out the 2.5 volt bias with the Hall effect sensor here. And with the resistors I've got here, a 220K and the feedback resistor and a 10K here, I get a gain of 22, and this is the output that I will use, and it gives me a range of between 0 volts and roughly 3.5 volts, I believe, for the typical voltages here I get out of this Hall effect sensor for a current range of 0 to 1 amp. I'll have to check those numbers. I think I'm incorrect here. But anyways, that's the circuit I've used here, and it gives me a usable output voltage here on the output pin of this op amp. So now here's the circuit again. This time I've changed the this meter here to read the output of the amplifier, and if I play with the potentiometer here and adjust it, you can see how it goes up in voltage. Now I just turn it until I get it down to the lowest reading I can get, and if I keep turning it, it doesn't change. So the output of the op amp has a bit of an offset voltage, which I can't get rid of easily here, so I just back it off until I see the voltage just starting to rise back down to the minimum. And there it is there. Now, as you can see, there's no current flowing in the coil yet. If I turn on the variable power supply, now I've got 0.5 amp and I'm reading 1.5 volts. Let's turn up the current here until we get up to 1 amp. So I was a little out of my readings. 3 volts. So 1 amp gives me a 3 volt output. 0.5 amp should be 1.5 volts. Well, I can't get quite down to 0.5 amp. Just under half, or just over 0.5 amp. But you can see how linear it is with the current. And I've got quite a useful output now. I'm not going to be able to go much higher than 1 amp here, because the output of the op amp is limited to something less than the 5 volts, the 5 volt rail that I've tied it to. It's just the nature of this particular kind of op amp. If I can try to get it up to 1 amp here again. I think with 5 volts in, with the 5 volts on the positive rail of the op amp, the best it can do is about 3.5 volts. So I could go a bit higher in current. And eventually that op amp's going to saturate and I'm not going to get any other readings. Oh, it's still going. There, it just stopped. So I can get about 1.2 amps out of it. 1.1 amps. 1.2, yeah. So my maximum is about 1.2 amps in the coil. So there's a very quick example of how to use the Hall effect sensor as a current measuring device. Previously, in the previous video, I used it to measure the rotation of a shaft of a motor by sensing a magnet passing by, and so I didn't need to use it in a linear region. I just wanted it to give me a pulse out every time the magnet's passed by the Hall effect sensor. And now I've used it to measure the magnetic field within a coil, which is proportional to the amount of current flowing in the coil. And now I've got a very effective current measuring device which can be placed anywhere in the circuit because there's no reference to the coil to anywhere else in the circuit, and that makes it quite useful. And I think in another video I'll show you how I use this to create a useful device. But for now, I think I'll leave this video as it is, and just showing you how to use a Hall effect sensor as a current measuring device. So I hope you enjoyed this video and got something out of it. And if you enjoyed it, give me a thumbs up on YouTube, and give me some comments to see, tell me what you think, and give me some ideas of what I could do with this current sensor. Anyways, thanks for watching, and I'll catch you the next time. Bye for now.